Hello guys, so now after we have modified our solver, we need to run it on a case to make sure it is working at all or working well as required. So let's copy the cavity case again and try to use it. Compressible, icoFoam, cavity. Let's copy cavity again. Control C, go to OpenFOAM and the run directory. Control V. So what we need to do now is add our new solver parameter into the case. So the first parameter is the thermal diffusivity. I'm gonna be using the thermal diffusivity of helium, which is 1.9 to the power of negative 4, or to multiply by 10 to the power of negative 4. So alpha, our dimension is meters squared per second as the viscosity, and our value is 1.9 e negative 4, which is 10 to the power of negative 4. Control S. Now the second parameter is the temperature itself. So let's copy the boundary condition for pressure, because this is a scalar field, so it's gonna make things easier to just modify it. So open it and change your parameter to T. It's not really important to change this, but it's nice to know what you have in here. And the dimensions, don't forget to change the dimensions. This is Kelvin, 1 Kelvin. And let's have our internal fields to the room temperature, which is 25 Celsius and 297 Kelvins. Let's define our moving wall to be the highest temperature of 350 kelvins, for example. So it's gonna be fixed value, and the value itself is gonna be 350. And let's have our fixed walls to the room temperature as the inner fields, which is 297. Control S. Now we have our temperature and thermal diffusivity. Now you think that we are good to go and we should only run our solver, but don't forget to set up the finite volume schemes and finite volume solution. So let's start with finite volume solution and add our temperature. I'm gonna be using the smooth solver for temperature, and let's add it at the end. Control V. This is here. Temperature. Control S. And let's go to the finite volume schemes and add our parameters. Remember, we have used the d by dt for temperature, so we need to add ddt temperature, and let's use the Euler method for now and add the divergence of phi and t. I'm gonna be using Gauss linear as well. Let's change this only to t. Control S. And let's add the Laplacian, which was Laplacian of alpha and t. Call that alpha and t. And I'm gonna use the Gauss linear, but corrected, not orthogonal. Corrected. It really doesn't matter, I'm just using corrected because we have a totally orthogonal meshing. So I believe that's it. So open your terminal, source OpenFOAM, and let's run our modified solver. Go to run, cd cavity, and let's start with meshing. Type block mesh. don't forget to check your mesh. I know it is good, we have done it before, but you need to run check mesh in your cases. Now let's run our modified solver icoFoam T and press enter. Oh, it's running, and it has done running, so it seems that our solver is running good. So let's view the results in bar view, parafoam dash built in, press enter. Let's wait for it to start and hit apply. This message is not really important. If you are using OpenFOAM 6, really you wouldn't find this message also. But if you're using OpenFOAM 4.1 like me, you will find it. Don't give anything about it. Go to the next time step and let's see our temperature. It has been generated. Oh, as you can see, the temperature is developing in the time steps until it reaches the end. If this simulation was any longer, you will find the temperature going to have a curve like that in the OpenFOAM. Now we have seen that our solver is running good and it's doing its job. And so now this was your OpenFOAM first modified solver, and it's now working. You can visualize, use the temperature, let's say in the calculator, and anything. You can use it as any OpenFOAM defined parameter. And this was how to modify and use your modified solver. So see you in the following video, guys.